coming back from our break, then we looked at assumptions that we've made using an F-test. So the most important one is that, yes, the YIJs must be normal. The variance for each treatment group population is the same, namely sigma squared, and all the observations should be independent. Now, if these assumptions aren't satisfied, you should be doing a non-parametric Kruskal-Wallis test that we're going to discuss below. But before we do that, I want to mention that when we reject the null, what we're concluding is that at least one of the treatment groups has a different mean than mu. But which treatment group has a different mean than mu isn't revealed. And for that, we can use the Bonferroni method. Now, I should say that the Bonferroni method that I'm using is a little bit different than the one in the book. The one used in the book is more of a pairwise t-test, where you're comparing all different possible two-sample t-tests. And what I'm doing rather is doing a number of one-sample t-tests. So essentially creating a confidence interval for each of the treatment groups. And once I have that confidence interval, so actually I should say a simultaneous confidence interval, so that once I have my alpha level for the overall test, so I'm saying that if the null is true, that let's say there's just a 5% chance for rejecting the null. So to reject the null means that at least one of the confidence intervals does not contain the true, does not contain mu, right? So the idea in Bonferroni method is that we need to make our confidence intervals 101 minus alpha over I confidence intervals. So, for example, if alpha is 0.3 and I have three groups, then each then I should be looking at three 90% confidence intervals. 90 is 1 minus 0.3 over 3 times 100% CI. So that is what we're going to do here. And let's just see this in practice here. So we have three treatments in our three treatment example. We have N is three treatment groups. We have alpha, let's say 0.3, so alpha over 3 is 0.1. And our cutoff is T n minus 1 degrees of freedom alpha over 3, which is 1.88. So then to write down our CIs, our 90% CIs, we're going to have the sample mean, which is, for the first one, is 2 plus or minus, so then 1.88 divided by root 3. And so we get three 90% CIs. And if you make a histogram of the means, as shown here, what you can see is that the group 1 and group 3 don't have overlapping 90% CIs, and so it's fairly unlikely that they have the same overall, that they have the same mean. So Here I just mentioned that my Bonferroni is a little bit different, but you're free to use the way that I do it or the way in the book. What I'd like to do next is the Kruskal-Wallis test, and this is a generalization of the Mann-Whitney test to 2 or more treatment groups. So recall that Mann-Whitney test was a non-parametric 2-sample t-test where we used rank sums. And so here again, we're going to have rank sums. So what we're going to do is we're going to replace all of our yi's with ranks in the combined sample. And then we're going to look at the average rank for each treatment group and the overall average rank, which is n plus 1 over 2. So we can write down the sum of squares between just using the same formula as before, but now we're using ranks. So we can compute this, and notice that if the null is true, and what is the null? The null is that the distribution for each treatment group is the same. So if the distribution for each treatment group is the same, then you would expect that the ranks for each of the treatment groups should be the same or similar, right? So the spread of the means, which is what the SSB measures, the spread of the means should be the spread of the mean ranks should be small if the null is true. So we're going to be rejecting if we get a large SSB. But SSB can't really be a test statistic because it doesn't have a known distribution. But SSB over sigma squared R, the variance of ranks, that is chi squared with I minus 1 degrees of freedom. The problem is that we don't know what sigma squared R is, but it's not difficult to calculate the sample variance of the ranks. So the sample variance of the ranks is, we have capital N ranks, so it's 1 over n minus 1 sum, and then each of the ranks from 1 to capital N, and then we subtract off the average rank. So remember that so the average rank is n plus 1 over 2. So then we square that. So that on the left side here we have the formula for sample variance of R, and then some algebra. You can show that this is n plus 1 over 12. So we get now the Kruskal-Wallis TS, which is something that you can compute explicitly, and it's chi squared. So you're going to be rejecting when it's large. So we ran out of time in class, but it's good for you to see how to implement this in R. And so if you go to B courses, there's an in-class exercise, which is actually a at-home exercise, I suppose. And I just want to point out just some quick things here. So you do some data cleaning. You want to make sure that the normality assumption is satisfied. Take a look at the box plot. You want to make sure that the variances are the same. Then you can compute the p-value. You can compute the p-value, and it's 6.88 to the minus 5, or just using one-way dot test with equal variance equal true. You can just get the p-value in one step. So R has a built-in ANOVA function, in case that the variances are not equal, you really should be using Kruskal-Wallis, but there's a Kruskal-Wallis type test, which is one-way dot test without the parameter variance equal true. But quite honestly, I'm not exactly sure how this works, so it's a little bit of a black box for me. I would rather just use Kruskal-Wallis, which we come to next. So Kruskal-Wallis is a non-parametric test, and you can calculate it explicitly using the formulas that we described earlier. And here's the p-value that you get. Oops. Oh my gosh. Or you can just use the built-in Kruskal dot test to get more or less the same p-value. So just notice that for the parametric test has a smaller p-value, which means that if the null is true, then you have a better chance of if the null is not true, you have a better chance of rejecting it. So that's to say that the parametric test has more power than the non-parametric test. So larger p-value means less power.